add my minute of thanks to the organizers on air to everybody else's. It's been a very excellent workshop and particularly fantastic to have so many world experts to listen to, and also the opportunity to talk to people that I know and people that I have just gotten to know. Jason, the work seems very interesting, and I'm looking forward to hearing his talk this afternoon. So it's Friday, and it's the end, and a lot of people are leaving soon. So this is going to be a talk with very little actual content. It's going to be a lot of sort of hand-waving.
You going to tell some jokes?
I might see if I can do that. I don't know. Right. I mean, there are sort of a number of questions around this topic of compactifications of moduli spaces. A number of questions around this that I've been sort of kicking around for some time, and I think there are other people who have been kicking around other aspects of these questions. And so I'm just going to try to give some overview of, what are some of what are the questions and sort of approaches to this question of topology and compactifications of moduli spaces. And there's sort of two motivations for me. One of them, of course, is conjectures like the Sen conjecture, which is about the L2 cohomology, or the L2 harmonic forms on these monopole moduli spaces. But there are actually a variety of conjectures of this type that relate to various sorts of hyperkähler spaces, hyperkähler moduli spaces, in which there are predictions about the space of L2 harmonic forms coming from physics. And so sort of from that point of view, of course, that gives you like a goal to try to understand. But what's from a different perspective, from the perspective of topology, this gives you the question of sort of a place to test out the question of what should Hodge theory look like in the setting of non-compact manifolds and non-compact Riemannian manifolds, because that's quite an interesting question. And by looking at examples, for instance, in the case of locally symmetric spaces or in the case of manifolds with conical singularities, this has led to some very interesting and rich topological theory. And for that reason, it's reasonable to conjecture that looking at natural metrics on other non-compact spaces may lead to new interesting ideas in topology. So there's sort of I guess, motivation from both sides of this. Okay, so the general question that I want to approach is, can we articulate an L2 Hodge theorem I should say, given a complete non-compact Riemannian manifold MG, can we articulate an L2 Hodge theorem of the form that the L2 harmonic forms on M with respect to this metric are isomorphic to, and I'm just going to sort of say, some sort of cohomology on some sort of cohomology. So this is of topologically defined cohomology, and this is some compactification. So, and possibly non-singular compactification, of course. So that's the general question that we want to approach. And let's just look at some examples. So these are very These are Friday morning examples. They're not very challenging. You probably know them all already, but we can still get some sense of the sorts of questions that come on by looking at these. Okay, so for instance, let's look at the situation where sigma is a Riemann surface. And P is an element of sigma, just any point on that surface. Okay. And what we can do is we can look at the punctured surface, and near that puncture we can endow the surface with a variety of types of metric, right? And so one thing that we could do is a cylindrical type metric. So
sigma is compact. You're deleting a point. Sigma is supposed to be compact.
Sigma is a compact. Right.
That's you said it. Sorry.
Yeah. So here's our puncture. Of course, around the puncture there's an S1, and what I've done is I've just near that puncture I've endowed it with at least an asymptotically cylindrical metric, or what's sometimes called a B metric. Right. So this is something that looks like dr squared plus ds S1 square root d theta. Right. So that's the metric there. And so this is quite well known that in that case, if you look at the harmonic forms, the L2 harmonic forms on sigma minus p with respect to this metric, this is equal to the image. Okay, so let's see, what can we do? Well, how we can compactify it, and I'm sort of going to choose my compactifications in various ways. But what I'm going to say is that the sort of the natural geometric compactification here is the one that you get by just adding on a copy here, sort of ad infinity, right? So that's something, so as when Les Saper was talking about the sorts of compactifications of locally symmetric spaces, he was talking about a sort of natural geometric compactification in which the metric induces a metric on the boundary. So at least up to a conformal factor. So this is a situation like that, where you've induced a metric on the boundary there. And okay, so in that case, if we call this X, this compactified thing X, then it's the image of the cohomology of X rel its boundary.
Sure, so let me try to understand. So you're just cutting in these coordinates r and theta, you're simply taking r less than or equals some capital A.
That's what it comes down to, right? Now, I mean, I'm
You could then change coordinates, but you're thinking of it as the interior of a manifold.
I'm thinking about this as interior of a manifold boundary, right? So, I mean, you can also rewrite this as dx squared over x squared plus d theta squared, where x goes to 0, and that's, like your r equals infinity, and I'm adding a formal copy at 0, right? So the metric itself doesn't extend, right? But it does induce this metric on the boundary. Yeah.
Topically, you're just writing the right-hand side now, which is topologically, it doesn't matter how you think about it.
Right.
Right.
So
On the right-hand side,
boundary,
there's no
that's
metric, right?
that's
So
independent.
when I say some sort of topologically defined cohomology, on the right-hand side, I don't want the metric to come into this. Right now, there may be other data that needs to come in, but it shouldn't be metric data. Yeah, that's right. So, I mean, this is also isomorphic to the reduced L2 cohomology, but for various reasons, the reduced L2 cohomology is not a good cohomology theory. So we want something that has good topological properties. Okay, so that's what we get in that case. We could also, instead of giving it a cylindrical metric, we could give it a cusp metric. Right, so this is the sort of metric that you get if you have a finite volume quotient of the hyperbolic plane, right? So this. Okay, so now once again we've got this theta, and here the metric looks like dr squared plus e to the minus 2r d theta squared. That's that cusp metric. Okay. And in this situation, if we look at the L2 cohomology, turns out to be isomorphic to the cohomology of your original surface, where now you see the natural metric compactification. If you add on sort of, what does it make sense to add on? Would it make
Put a
sense
dot there, but it's actually maybe the first cohomology is the one you're interested in, right? So I mean, you are going to have problems like H0, for example, or
No, it's true in all degrees.
true in all degrees.
Yeah.
Because you explained it there.
So the natural metric compactification here, of course, is just adding that dot back in, and that just gives us back our surface, and that's what we get. And finally, we can look at a G ALE metric in a sort of two-dimensional sense, right? Which is what the So this is where, well, okay, it doesn't have to be, it can be any volume of cone, but basically you've got the large end of a cone. So I should make that curve, right? I should make it. So now where you stuck the large end of a cone on. So of course this is dr squared plus r squared t. And in this case, if you look at the L2 cohomology, okay, I'm having the same problem that Laura had, but remembering what I told her, I'm going to try this, see if it works for me any better than it did. So in this case, once again, it's maybe not so clear what a metric compactification would be because there isn't anything that gets small, right? But what we're going to do is just add on again. Just think of this again as the interior of a manifold with boundary. Okay, so once again, this is our X. And in this case, this is isomorphic to the following.
You don't mean cusp.
I don't mean cusp, thank you. I mean ALE. Thank you very much. So now, when we look at the zero cohomology, we're going to get, the absolute cohomology of X, and, is that right? No, we're going to get the relative cohomology, sorry. And in the top degree, we're going to get the absolute cohomology, and in the middle, we're going to get the image of one and the other.
So I guess conformally, this one looks the same as the first example.
In fact, they're all conformally.
No, isn't one minus a disk versus one's minus a point?
You have the hyperbolic infinite area, then it's the disk.
So, I mean, basically, if you've got a surface, then they're all
I see.
conformal, right? They're all conformal. Okay. So, and that's an important. That's actually one of the things I was just going to make some notes here.
I see.
So.
H1 will be the same for all.
Yeah, excellent. Gold star. No, that's good. That's good. He does have a tendency of answering the questions that you were about to talk about. Did he do that to you too?
It does it all the time.
Does it all the time. It's great. No, it's good. You must have been your best student, favorite student. That's good.
No, I was considered the nightmare student.
Yeah, man, I would be so excited if any of my students. Anyway, okay, so.
You say that, but
Yeah, maybe that's true. Okay, so these are all conformal. Equivalent. And it turns out that middle degree L2 cohomology, middle degree L2 harmonic forms, that is a conformal invariant. Because if you look both in terms of the Laplace operator and in terms of the volume versus the size of the forms, these things cancel. The scaling factors cancel out exactly in the middle degree. So these all agree in the middle degree. Another thing that we can mention, of course, is that because the L2 harmonic forms for a geodesically complete metric, these are always the same as the kernel of d k mod the closure of image d k minus 1 in L2. This thing here is only determined by L2 and not by the specific metric, right? Only by the metric that is induced by L2. So what that means, right, so this only depends on L2, not on G itself, not on G sensitively. And two metrics that induce the same L2 are called quasi-isometric. So So that means bounded within each other, right? So each one is bounded by a constant times the other on both sides.
The actual complexes are always defined in terms of smooth forms intersect L2, right? Is that the...
Well, you can, right? Although, you can do it that way. Although I would say that generally now it's fairly standard to extend those to complexes of L2 forms, and you just have to make the requirement that both the form and D of the form are in L2, right? And that's the sort of standard Hilbert complex framework in which you can talk about this, right? Because otherwise, of course, the closure doesn't, I suppose you could take the closure with smooth things in both cases, but people tend to do this within the framework of Hilbert complexes. Yeah.
You hope to show that there are smooth representatives anyway, so that whether you complete it or not will be...
Well, there are always going to be smooth representatives because of elliptic circularity on the interior, right?
No, I can see this. It makes sense.
Yeah. So, okay, so what does this mean? Well, this means that up to isomorphism, this space doesn't depend on G, except for up to quasi-isometry either. Although, of course, the actual harmonic forms do depend very sensitively on the metric, right? That there's this sort of miraculous thing that if you're just looking at sort of dimension of the space, it only depends on the quasi-isometry class of the metric.
Sorry, just to be clear, Eugenie, is that a theorem or a definition? I mean, in other words, the curly H thing is the L2 harmonic forms.
I wouldn't call it a theorem, maybe a
It's not,
lemma.
I mean, the left-hand side is...
However,
Maybe-
this was a 100-page paper by Kadira in 1950.
Oh, was it? Okay.
So, yeah.
Okay.
Back then it was a theorem.
Back then it was a theorem. Now it's maybe a lemma. It's not very difficult.
But script H is the L2 harmonic forms.
I'm sorry?
Your script H is the L2 harmonic
Right,
forms.
oh, yes.
This is like,
Yeah, sorry.
What the hell is he doing?
Yeah, this is always the L2 harmonic forms.
Jesus.
Yeah, okay.
Right, so as I said, those do depend. Of course, the actual
Yeah.
representatives depend very sensitively on your metric. But miraculously, because of this relationship, the dimension of the space only depends on the quasi-isometry. Okay. And the third, let's see, one more comment. Okay, and the third thing that I will note here is that one of these theorems is not like the others, right? And I hope that you recognize which one that is.
That takes us back to the question that Michael just asked. Which are the theorems?
Sorry, yeah, I guess these are each theorems. So, yeah. I haven't even bothered to give them names because I think that, let's see, who would have first proved these? I mean, this is certainly a special case of the Atiyah-Patodi-Singer index theorem, so Atiyah-Patodi-Singer work. And in this case, this is something that that Richard Melrose has in his paper on scattering, but perhaps was known before, maybe? Certainly was known before, right? And I mean, the cusp again, that's fairly well studied metric on the, that's
Silver knew it.
Selberg. All right, thank you. My history, it's terrible. I really need a history of moduli spaces class or something. History of
Riemann surfaces.
Riemann surfaces, exactly. Okay, yeah, these are quite old results, but they're still informative. So, okay, so the one that I would say is not like the others is this one here, right? And the reason is that whereas the others, I can just write this dot here, right? I can't do that here. Right? So this is a sort of unsatisfying result, right? So the ALE result is unsatisfying because it depends on degree. And what that means is that whereas in the other two cases we can relate the harmonic forms to a complex, to a particular complex of forms, we can't do that here. We have to choose different complexes to relate them to in different degrees, and that's just ugly. It's just ugly.
I mean, complexes that somehow don't depend on the choice of metric. Right? You could always say that you've got this.
Right, yeah, I mean, you, on this side you can, so I'm going to give you generalizations of these to bring in some new ideas. So, first of all,
So all of the examples you gave in Riemann surfaces, conformally the thing is just a punctured Riemann surface. But you
Yeah.
could also look at things where you took out a disk instead of a point.
those wouldn't be conformal anymore, right? Okay, so there's only two conformal classes, right? They're the incomplete ones and the complete ones. So any complete ones are conformally equivalent, any incomplete ones are conformally equivalent, but you can't turn a complete one into an incomplete.
So you could definitely, on the other hand, choose a metric which makes one makes it
Incomplete.
look like into a complete
Right,
manifold.
okay, so I've just erased this model, but maybe you can sort of see it in the chalk dust here. And the reason that I'm considering the case of geodesically complete non-compact manifolds is that if you look at geodesically incomplete manifolds, so manifolds where there's some corners or boundaries, the problem is that suddenly this object on the right-hand side isn't a well-defined object in general.
No, but I was imagining you could take a Riemann surface minus a disk, and then you take a conformal factor that blows up as you approach this circle.
Oh, yeah. Well, and that's effectively what we're doing here.
No, but this is a punctured Riemann. I mean, that was what I was confused by. These are all of these are punctures, right? Conformal.
Yeah, but I mean,
But if you had instead, is there any significant difference if you had, you cut it off at the disk and now change
Yeah,
it?
so the answer is different then. Yeah, so this is an infinite area Riemann surface. Yeah,
Oh,
hyperbolic metric, and then the answer is sort of inverted to what the ALE of the one.
Oh, sorry, you were asking about the infinite volume hyperbolic.
Yes.
Oh, yeah, that is different, and that's even more interesting because, of course, then the H1, there are infinite many,
Yeah, that's what I was thinking.
infinitely high dimension of L2 harmonic forms in middle degree. Yeah, that's right. So it's the same in these two degrees, right? But here it's actually infinite dimensional. Yeah. Okay, so. All right, so I'd like to sort of generalize these. Okay, so first of all, this example with the cylindrical, this generalizes in a quite straightforward way to this Atiyah-Patodi-Singer theorem, or at least it's in their paper from 1983, right?
No.
70.
73, gosh. Sorry, thank you.
How time flies when you're having fun.
Okay, so and in that case, what you can do is you can just say that you just have any manifold with boundary, right? So instead of your X being having an S1 boundary, it can have any boundary at all, right? So this gets replaced with some boundary B, right? And so this just becomes metric on the base, right? And then you get the same result there. So that generalizes to a general cross-section or a general boundary. So for the cusp metric, we can generalize that. Well, first of all, these look like the simplest versions of locally symmetric spaces, right? So one generalization is, of course, to the entire class of locally symmetric spaces, where they have this sort of cusp behavior. I'll talk a little bit more about that. But if we even just bring it up 1 degree, so we can look at a fiber cusp metric. Right, and so that's something of the form Okay, so now we've got a manifold M with a boundary, or let's say X is a manifold with boundary. No, that's not right, sorry. So it's got boundary Y, sorry, and Y has got some vibration structure. So what you can imagine, for example, is if you, instead of looking at a Riemann surface and taking out a point, if you look at a smooth variety and you remove a smooth divisor, right, then you would have the normal bundle of that smooth divisor as your, the unit normal bundle of that smooth divisor is your boundary, and there would be the natural base would be your divisor, and the disk in the disk bundle would be your link. So then, I used to try to draw a tori, and then I realized that it's better just to draw a rectangle. So this is my example of a fibration, right? So this is Y, and this is B. B is my base, that's the horizontal direction, and F is my fiber, that's the vertical direction, right? And so, the base is just going to continue out to infinity, and the fibers are going to have this cusp-like behavior as you go out to infinity. Okay, so the natural way to compactify this, of course, is just to put...
So these curved lines are like the unit
Sorry?
normal vectors above the base in the fiber? Is that what the curved line is supposed to be?
Well, yeah, okay, so
The radius of the fiber.
that would be your fiber, right?
Yes,
And then
the size
as your
of the fiber.
fiber, as you go out, the radius of your fiber shrinks, exponentially. So, of course, once again, you can just put in that copy of B at the boundary, and as Les Saper was saying, this is a natural metric compactification, because again, if you look at this layer here, it defines a natural metric. This is the thing at the boundary where it defines a metric, because this guy has vanished. Okay, so this is a natural metric compactification to use. Okay, so I guess I don't really want to do. Okay, so all right. So what he called so we'll let x hat then be the analog of his x hat, which was his reductive Borel-Serre compactification, right? So it's x union a copy of B, at infinity, basically. Okay. And in that case, we end up getting that the space of L2 harmonic forms is isomorphic to this thing. Oops.
So Y is just an end of X in this discussion.
Y is just an end, yeah, right. Well, you think of it as boundary, right? So in the same way that we thought of B as our boundary.
So once again, the example to keep in mind is I have a divisor, I'm cutting out the normal bundle.
That's right. In that case, you're linked with
disk bundle around the divisor, and the boundary of that disk bundle is Y.
the boundary of that disk bundle is Y,
Okay.
right? The disks are the L, right? The spheres are the L.
The spheres of the, yeah, got it.
Yeah, right. And so in that case, you would get a sphere here. But more generally, it doesn't have to be something that compactifies to something smooth, right? So in general, this x hat is not going to be smooth, because if you take a cone on something other than a sphere, that's not smooth anymore.
Right. And that's, by the way, an equal sign, not a minus sign? I mean, x hat is equal to.
Equal to, yes, thank you.
Okay, good.
Okay. Okay, so what is this? All right, so this is the first sort of new cohomology we're seeing, and at least it's not that new. Okay, so this is cohomology. So this is intersection cohomology. And this was developed in the 1980s. Okay, so the first paper of Goretzky and McPherson came out in 1980. But there was quite a lot of interaction between the work of Goretzky and McPherson, who were developing a homology theory, actually a singular homology theory, to use for singular spaces, with Jeff Cheeger, who was looking at L2 cohomology for conical manifolds with conical singularities. So this is
It's a boundary term, so what if you, the first one is IH of x hat with respect to D or something?
No, there's two different.
Oh, there's N and M. Oh,
N and M, right.
sorry.
So it turns out that these cohomology theories, there's not a single one. They're parametrized by a quantity or by a vector called the perversity. And there are sort of two perversities in the middle that are Poincare dual to each other. Okay? And in the event, that you have vanishing of certain things, in particular, for instance, if L is a sphere, right, then these are the same. In fact, if L is a sphere, this just reduces to the regular cohomology of the compactified, the smooth compactified thing, right? So, so this is related to L2 cohomology for manifolds. These are incomplete metrics, right? So manifolds with iterated cone metrics. So this is work by Jeff Cheeger. There's a very nice sort of revision of this, or revisiting of this work by Rafe and Pierre Albin and Lechtnaam and Katza, is that right? So they've got a very nice paper in which they revisit this theorem and sort of prove it using using a different type of sort of more, I would say, a more contemporary family of analytic techniques.
There's several papers.
Is
Right.
it
Well, several.
So it's a topological cohomology.
Yeah, that's right.
And a homotopy invariant. I mean, it's homotopy.
The stratified space.
It's
Okay.
a stratified homotopy invariant. That's right. And well, in fact, it's even more than that, right? Because it turns out that it's independent of stratification. Yeah. So that's why if you remove the stratification and you get something smooth, it's just the smooth cohomology. Yeah. So it's quite a remarkable theory and a very very beautiful cohomology theory that I definitely recommend that everybody learn right now.
I don't know anything about it. Is it a generalized cohomology theorem? Does it have a classifying space?
I believe it does.
Yeah, I think so. I mean, it
So,
really,
so when you
it sort of does, well, at least middle perversity will have everything that you want it to have.
So it satisfies the axioms of the generalized cohomology.
like Heidelberg,
Yeah,
Well,
Yeah.
Changing the axiom for the point, right?
Yeah, exactly.
Yeah, I mean, basically, it replaces a Poincare, the local Poincare lemma, by a revised one. I'll talk about that in a few minutes. Okay. Now, it's also possible, okay, so more of relevance
So,
to,
I mean, I presume the N and the M are determined. I mean, it can't be true for all. I mean, that.
N and M, okay, right, so maybe I should call them like N bar and M bar. These are specific perversities
Right, I mean-
called the lower and upper middle perversities, yeah, so.
And there's a canonical map between them?
Yeah. So, all right, so what we can also generalize this one, and this is the one that is more relevant to these gravitational instantons. And this is the paper that Rick and Tomasz Hauser and I wrote several years ago. Maybe not that many years ago, but it feels like so. Over 10, yeah. Okay, so I just think of it as pre-children or post-children. It happened pre-children for both of us. So what is the metric that we look at here? Well, okay, when we generalize this, okay, so notice that when we looked at the cusp metric, we put the cusp in the fiber, and we put that over a constant size base. Okay, but of course, as we know, in the setting of the ALE, ALF, and ALG, not with stars, with no stars allowed. I'll talk about those in a moment. But in the setting of these, the metrics are always of the form up to quasi-isometry, which of course is all we care about in this setting. dr squared plus r squared times some metric on a base plus a metric on a fiber. Okay, so now, right, so the pullback from the base. So once again, you've got a fibration structure near the boundary, and ALE, of course, well, ALE is really just this one here, but if you look at ALF and ALG, ALF is a situation in which your fiber is an S1, ALG is the situation in which your fiber is T2. Okay, so what we're doing is now the fibers have constant size, as we know, and it's the base that becomes big, right? And so, we'll draw a picture of this. Okay. So once again, we start out with our rectangle, right? Here's our base. And now what we're doing is we're putting a cone, a big end cone over that, and we're just keeping these fibers equal size. So you can sort of imagine it, something that looks. And, as this one doesn't extend well, I mean, this one is kind of a stuck together hodgepodge. So the result here is also a stuck together hodgepodge. And I'm just going to write
That's a joke,
it.
right? You're doing Hodge theory rather than Hodge theory.
I'm doing Hodge theory rather than Hodge theory. That's right. Okay, but we're going to compactify in the same way as we did before, right? And the reason we do this is that, in fact, this is a conformally equivalent metric to this metric. And so, in order to make there be
different R's, yeah.
they're different R's. Yeah, that's right. Right. In order to make this metric be something that, in any sense, gives a metric on any, at infinity, you can't let this thing blow up where it's not, in any sense, a meaningful metric, right? So you rescale it down to that guy, and you give it the same compactification. So in this case, we get so now, all right, this is the image. Okay. Okay, so I'm writing this in sort of a cheap way, right? But the point is that now, rather than having just a fixed perversity here, right? And fixed perversities correspond to a proper chain, cochain, right? The cochain that we're drawing out of for each of these comes from a different perversity, right? So depending on the degree, we have to choose different perversities. Okay, so once again, it's not coming from a relationship between the L2 complex and any sort of any single complex on this topological object.
So I'm just trying to connect this to things I know. I mean, if you take in the ALG setting, there are a lot of examples where you actually have compactification of M as a compact complex surface. when you look at where you cut out a divisor, it's very much like what was being asked before. What would, so this intersection cohomology would actually be ordinary cohomology in that case? But what do you do, how do the perversities arise? You're just saying, I guess you're just saying it would simply be the ordinary second cohomology. I was thinking it was the second one of the compactification.
The second, well, the middle one
Yeah.
will always be the middle perversities, right? Because the middle degree is always conformally invariant.
Right.
And so,
So if
it
X
reduces
is,
to this same thing.
X is smooth, I'm thinking of cases where you're actually
In the
just
middle
taking-
degree, if X is smooth, then you just get regular cohomology.
And this, I see.
Okay, so this is sort of the state of art as of 2004 or something, 2003. Okay,
So
so
if X was instead an orbifold, instead of something smooth, does that, do the perversities enter at that?
yeah, for orbifolds, it's the same as the standard orbifold cohomology as well. Okay, so, all right, so so we've got these cases in which we know what's going on, right? And I guess I was going to put in an advertisement for something related to Jason's talk later, which is that if you look at the universal cover, of the Hitchin manifold, right, and you apply this, right, that the associated X is Cp2. And it's smooth, and that's kind of nice because this actually, here this is a hyperkähler thing, and this is Kähler, right? Except that it turns out that the complex structure here is totally different from the complex structures here. And you can see this because whereas the SO3 action on here, the SO3 action on R3 here rotates the complex structures, the SO3 action on here that you sort of get as the analogous one preserves the complex structure. And so I guess Derek and I were talking about this yesterday. He says that Hitchin has a paper in which he looks at a family of metrics on this space, where on one end you get the restriction of the metric from here, and on the other end you get the Atiyah-Hitchin metric. So I mean that's sort of in terms of this question that Jason's going to talk about, which is, can you get a nice, can you get your complex structures? Can you get these structures to extend to some, to a boundary, to some sort of compactification or beyond the boundary?
Yeah, I think that
This is a very interesting setting, but I think, it sort of does bring up the question, is there, can you do this in any more general sense? Is there any other, is there some compactification of some of these other hyperkähler moduli spaces that carries some sort of special structure, though, which perhaps isn't the same as the special structure that the original thing had. So that's very strange. I don't know what to make of that, but it's
If I
definitely an
remember
interesting
correctly, I think
phenomenon.
the complex structure on CP2 is even actually, the orientation it determines is the opposite one from the hyperkähler complex structures.
Yeah,
So it's
That
really,
sounds
in
right.
some sense, the compactification is CP2 bar, it's with the other orientation.
yeah. Yeah, so it's, at any rate, but it's a very strange phenomenon here, and certainly, as I said, I guess Jason's going to talk about things along these lines later this afternoon, so as I'm looking forward to that. Okay, so well, we had these two examples, right? These were the ALF and ALG, right? But when Han talked a couple of weeks ago, he talked about these new constructions of gravitational instantons that he called ALH star and ALG star, which I had never seen before, and these were kind of very interesting to me because they relate to some things that I've been looking at. And so he's looking at a situation. So in one case, let's see, the volume growth. I looked at the volume growth. Now I've forgotten what it was. Okay, so ALG star, I think, basically looks like this. So okay, so this is interesting.
Is it log or log squared?
Oh, it's probably log squared.
You want it to be positive.
I'm sorry?
You want it to be positive, it better be log squared.
It could be.
This is asymptotic.
This is
No,
asymptotic.
but
is
R
our
is large.
definition.
R is
Right.
large.
Yeah.
Very big.
So, okay, so this is very strange. So, of course, all right, so we have the same picture in the base, right? We just have the same cone, big N cone in the base, the same Euclidean space in the base. But here, okay, now I'm just gonna look, I'm gonna ignore this direction. I'm just gonna look at one point here, right? So now in our θ1 and θ2 directions, right? So if this is θ1 and this is θ2, have I done that right?
Depends what comes next.
I think I want to do it the other way around. Okay. As you go out, θ1 is growing ever so slightly, right? But θ2 is
Keeping the area fixed, just exactly.
right,
Yeah,
but keeping the area fixed, right? So, right. So, okay, it's not a good picture. Not a good picture at all. But modulo the poor quality of my artwork. So basically the rectangle is keeping constant size, but it's scaling.
Getting very standard.
And for scaling. Right, and then there's a similar phenomenon that these. Yeah. Yeah. Really, I recommend that you look at the talk. It's really, he's got a very impressive, I think, new construction of these things. Fine.
First
Yes.
month, yeah,
Monday, the first week,
The very
talk.
first day,
Yeah,
yeah.
yeah.
20th of July.
Okay, so he also talked about some ALH.
So what's the answer?
What's the answer? I don't have an answer, but because I just heard about it. Yeah, well, if I end up writing a paper about the answer, you can put that into your report. At least that I have a,
There you go.
There's a sort of natural compactification, because the way he cooks these up is by cutting the divisor out of a surface.
yeah. So it will be very interesting to see if we can make the connection there. So and here, as I said, there's a similar sort of thing. It's just different scaling factors, right? There's an R and a R to the 4/3 and an R to the -4/3. Okay, so let's see, finish that. Okay, so what we see here is a situation, and this is one of the issues that I've been thinking about over the past several years, and in a sense, what we started with when we started with just the like for instance here the manifold with boundary with a cylindrical metric, we have a situation in which there's a lack of isotropy in the end in the sense that looking away from the boundary is different from looking inside the boundary. But in a sense, in terms of the scaling of your metrics, everything in this boundary is scaling in the same way, right? Then when we move to the fiber boundary and fiber cusp setting, suddenly we have a situation where depending on if you're looking at a fiber direction or a base direction, your vectors scale in a different way, right? And so this is even more anisotropy in the sense that every direction you look, the scaling is different. Okay. So the question is, how can we build something that will capture this sort of phenomenon in which fibers, different directions are scaling in very many different ways. So, problem. Question. How do we capture anisotropy in the metric in some topological manner? Right? And so I would say that if you have a singular space, it's very natural to have three different directions because for every stratum you've got the base direction, the link direction, and the radial direction, right? So there are sort of, in the topology, three natural directions, and that's why, in a sense, when we're looking at the fiber cusp and fiber boundary, it relates very naturally to this cohomology on singular spaces. But when we move to a situation in which there are more, well, then somehow we're going to have to add some information to our singular space, some sort of topological information on top of that singular space to be able to tell apart those different directions in the fiber, because the topology by itself doesn't remember that, right? Okay, so you can ask, okay, so where are there examples of this that have been done before? And the answer is yes, there are examples of this that have been done before. So in the setting of locally symmetric spaces, so remember, I've sort of related some of this to locally symmetric spaces, but if you remember Les Saper's talk, as you approach any boundary hypersurface in your locally symmetric space, right? So as you approach here, you don't just have a single fibration. You can have any number of fibrations. So what you've got is, T, K1 over some Y1, to T, K, L over some Y, L over some base, right? So this is your right. So in general, there's a whole stack of fibrations, and these fibers, these torus, these no-manifold fibers, and their metric, the metric here looks like dr squared plus, this is your overall pi or phi over star dsb squared, and then plus h's that come from each of these, and those scale like e to the minus 2 wi dStkL, squared. Okay, so where these are the allitherant weights that you get. So according to the representation theory, the Lie theory, and how that acts, these things are going to scale at different rates.
U to minus W2I times R.
Times R, yeah, sorry. Thank you. Okay, so I guess this gets, since I'm coming up on the end, this gets to the original title of my talk, which is multi-controlled spaces, cohomology of multi-controlled spaces, okay? So, this is work that I set my PhD student to, and we've gotten towards the end of at least the first version of this is, okay, well, I should backtrack, okay. Okay, so in the setting of locally symmetric spaces, there is a cohomology theory that captures this different behavior. And this is called weighted cohomology. This was introduced by Goretzky, Harder, and McPherson in, I think, not very, like 91, 92? Oh, I had it written down, and now I don't see it. Oh, no, okay, sorry. Okay, actually, I can do this. No, oh, yeah, 1991, okay, so Harder, Goretzky, I suppose it should be alphabetically Goretzky, Harder, and McPherson in 1991. Okay, so I'm sort of putting into this theorem a definition as well, right? So first of all, they define a weighted cohomology. Now this is the metric compactification. This is the reductive Borel-Serre compactification. Okay, so not the Sutta K compactification.
So this is always for a locally symmetric space.
It's for a locally symmetric space, right? But first of all, this weighted cohomology. Okay, so not to be confined. So not L2 weighted. So this is weighted in the sense of Lie theory, not in the sense of weights, of L2 weights. So they defined weighted cohomology on the reductive Borel-Serre compactification for any locally symmetric space, not just for Hermitian locally symmetric spaces. And then they showed that in the case of a Hermitian locally symmetric space, they showed that the they showed that that this weighted cohomology with a particular middle weight on x hat is isomorphic to the intersection cohomology in middle weight of this such a K compactification. And of course, Safer, Stern, and Loughborough had proved that this is the same as the L2 cohomology of the original locally symmetric space with respect to its natural metric. Okay, so, all right, so I guess there's a conjecture here. So this is true. So we have this relationship in the setting of Hermitian locally symmetric spaces, but it's not known for general locally symmetric spaces whether this isomorphism still holds. Okay. So as I said, I've been sort of looking at things related to this. First of all, trying to build some analytic tools that can deal with these multiple fibration structures. That's joint work with Daniel Grieser. And simultaneously, I've had my PhD student, who's just about to finish, working on generalizing this concept of weighted cohomology to settings other than locally symmetric spaces. And so that's also recent work that I've been pursuing in this direction. Anyway, so thank you very much for your attention.
Thank you. Questions for us?
So how do you formulate these weights topologically? I mean, do you have some sort of sheaf over the?
Right. So this is this multi-controlled structure, right? So you have to, as I said, that the topology of the compactification, the topology of the stratified space by itself, won't remember that the link itself was fiber, right? So the first thing you have to do is define something, an analog of control structure, which we call a multi-control structure, which dictates that there's some multiple fibration structure rather than a single fibration structure, okay? And then it turns out that you do need to make some condition, well, okay, so then what you can do is near that stratum, right, you just choose horizontal bundles, right, and you can use that to define these, to decompose your
So it's splitting your tangent bundle as you go.
You split the tangent bundle,
some
right?
jet of the splitting the
Yeah,
tangent
yeah,
bundle at the boundary.
That's right. And then you have basically a requirement that, that sort of says, if you add, you can either add, one of these guys or two of these guys or one of these guys, right? That sort of the cost, as it were, the L2 cost of adding, it relates to the L2 cost, right? But that, that the degree in these is not, it's not, a fixed degree bound. The degree depends on, right, how these things relate. And right, and then, okay, so you can define that. Obviously that depends not only on the multi-control structure, but on the choice of horizontal distributions, but you can show that in the case that you have sort of very nice bundles, they're flat with respect to various things, and then in fact the local cohomology doesn't depend on those choices, right? So
Does the proof of this theorem depend on thinking of this compactification as an complex algebraic variety, or in the case of Hermitian symmetric spaces?
So this is Safer, Stern, and independently Loughborough, right, in 1990, right, and this is the Goretzky-Harden-McPherson, and both of these, yeah, well, this is it's not a straightforward calculation, right? So, one of the things that's interesting is that there are actually two middle profile weights here, right? And it turns out that these two, the local calculations for these two are not the same. But because of sort of global, the way these things fit together globally, they end up being the same overall, right?
So these are dual to each other, did you say?
These would be dual to each other, yeah, but it turns out that, although they're local, although the Poincare lemmas, if you think in terms of the generalized cohomology, what is the Poincare lemma you're defining? The Poincare lemmas are different, right? Nevertheless, on these particular spaces, because of sort of vanishing of particular parts of the cohomology, they turn out to be the same. And basically, in general, this whole proof here as well, okay, so it turns out that in this case, the L2 cohomology is actually finite dimensional, right? So they actually prove this. But once again, it's not the situation that you just do the local calculations, right? There's some sort of miraculous vanishing as you glue these things together that makes it work. And it is intensely related to the Lie structure, to that algebraic structure.
So in terms of the Poincare lemma, you have different Poincare lemma at different points, just depending upon the structure of the, or is it the same everywhere?
Right, okay, so for any given stratum,
Yeah.
there is a consistent Poincare lemma. But on different strata, there are different Poincare lemmas.
Right, so that's different from a generalized cohomology theory where you have sort of a consistent cohomology at a
Okay.
point. Yeah.
Sure, yeah, so it's different.
Thank you. Anything else? Oh, yeah, sorry.
I had two questions. One is, what's known about the L2 cohomology of monopole moduli spaces?
Well, that's sense conjecture, of course.
Well, no, that's just one special example.
Oh, right, okay. So, well, there are a number of conjectures about various ones, and I don't, off the top of my head, know all of them, but I know that there are a number. And what it reduces to, actually, in the case of the the standard monopole moduli, the SU2 monopoles on R3, according to a theorem, the theorem of Gibbon, Siegel and Selby, thank you. Siegel and Selby, if the L2 cohomology is isomorphic to the image of relative and absolute, then that satisfies sense conjecture.
I was really asking if there's been anything post-Siegel and Selby.
Well, Hitchin proves that that's true in dimension, in the charge 2 case. So that's known in the charge 2 case, and you can also reprove it using the results that about fiber boundary metrics. But this is something that I've been working on with Derek, this question. And I mean, one of the issues, of course, is that the metrics, you don't have to know much about the metric, you just have to know it up to quasi-isometry. But even that is not yet established, at least Roger.
Roger's established it.
Unless Roger has established it, that's right. But I eagerly await the appearance of his paper.
Various of us are working
Yeah, and
on the,
yeah, that's right. So of course, there's also a structure that comes out. So I mean, I think that there is a conjecture about what it should be, what that metric should be, and so I guess there's also some work that Anda and Rafe have done on these QAC spaces that, okay, it's not fibered, so it wouldn't relate to that, but it does relate to these sort of, it's a generalization of QALE spaces, and they've proved some analytic results about the Laplacian on QAC spaces that could be used in general to get at something for sort of QALE.
These apply to L2 cohomology of L2 kernels of Dirac-like operators more generally?
Okay, so yeah, I mean, you can ask about that as well, of course, yeah. And the analysis, it will depend a little bit on the structure of that operator, but yeah, there are certain conditions that need to be satisfied. But the same sort of analysis that the same sort of B-calculus yoga stuff can be used to look at Dirac operators or any sort of Dirac operator.
Sounds like there are a lot of new techniques.
Yeah, well, I think that they were some of them developing sort of simultaneously, but yeah.
My other question was, my vague understanding is that intersection cohomology is introduced to have Poincare duality.
That's right.
Spaces.
Yeah.
So now, there's an interesting generalization of cohomology called Lie and Cheever-Simons or differential cohomology. And it, for nice smooth spaces, it has a lovely Poincare duality, and this is the essence of electromagnetic duality for abelian gauge theories. So I was kind of interested in how that generalizes to manifolds with boundary, and for physics reasons, you would want to have an L2 theory of differential cohomology, which I've never seen.
I don't know anything about that, but I would be delighted to get a reference from you after the talk. That
Well,
sounds
no,
really
it
interesting.
doesn't, well, for the
For the smooth case.
cases that, yeah.
Yeah, yeah,
that would
yeah.
be a reference.
No, no, that'd be great. Yeah, I'd be very interested.
But
to
it
hear
doesn't
about
exist for manifolds with boundary.
that. Yeah,
As far as I know.
Yeah, it hasn't been worked out yet.
yeah.
Okay.
Well, that sounds like an interesting
there's
thing to look into.
There ought to be some version of point collinearity for L2 differential cohomology.
Yeah. Well, that sounds very interesting. So, yeah.
Anything else, guys?
Is there any interest in biharmonic forms?
Biharmonic forms.
I mean, this theory that you've described seems to be focused on harmonic forms in the sense of the Laplacian is the underlying fundamental elliptic operator.
Mm-hmm.
So, and that may be for fundamental reasons that physics
Mm-hmm.
equations of interest have that, but are there instances where biharmonic operators appear in similar types of questions of resolution of singularities and all this type of infrastructure?
I haven't seen that. Although, I mean, I don't know. Can you look
Well,
at
there
biharmonic
are
things?
these Panitz operators, these fourth order Panitz operators, and actually there's some nice results about the null spaces of those, and so on. So that's.
I can imagine that you could use some of the same B yoga.
Well, so, yeah,
sort
well,
of
I mean,
settings.
the basic analysis is fine, but then sort of working out. I mean, so Kahn theorem used these when sort of describing non-L2 harmonic forms on convex Copenhagen manifolds. So you get that turned out to be a tool.
So the picture in my mind is maybe rather naive, is that these singularity structures, if you imagine now interpolating and having a weighted energy structure, which was basically penalizing gradients, L2 in the gradient and L2 in the Laplacian, then this offers a way to regularize the singularities of your lower order theory. So that's kind of why I was asking.
Okay, thank you, Eugenie.